Alright, here we go with iChem number 29. That should actually say unit 8. It's our last iChem of just the solutions part, and then we're going to move on to acids and bases. This principle is what will allow us to make ice cream on Thursday. So, what are colligative properties first by definition? It's a physical property of a solution that differs from the physical property of the solvent. So solution versus solvent due to the presence of the solute. The number of solute particles determines the severity of that property's change. How we measure that, we use molality. Because remember, it's the moles of solute over kilograms of solvent. That solute to solvent ratio is important for colligative properties. So there's two colligative properties we're going to focus on. One of them is freezing point depression. The freezing point of a solution will be lower than the normal freezing point of the solvent. So depression, freezing point depression decreases the freezing point. An example is salt water freezes at a lower temperature than pure water. So if we're talking about in the winter when we salt the roads, the purpose of this is to decrease the freezing point of water to decrease the likelihood of having ice on the road. Boiling point elevation is the opposite. The boiling point of a solution will be higher than the normal boiling point of the solvent. So in elevation, boiling point elevation increases. Okay, so adding solvent both decreases the freezing point, lowers the freezing point, and makes higher the boiling point. An example would be this: if we had salt water, it would actually boil at a higher temperature than pure water. So the same salt solution, lower freezing point and higher boiling point. The equation that describes this is delta T, the change in temperature for freezing or boiling, is equal to the constant Kf or Kb, depending on if we're talking about boiling or freezing, times the molality, which we now know how to calculate, times this value I, which is the number of ions present in the solute. I is only really important when you have an ionic solute, and we'll see why in a second. So delta T is change in temperature, Kf is a constant, Kb is a constant, you use F for freezing, B for boiling, molality we know how to find, and I we'll talk about in one moment. Okay, so finding this number of solute particles. In an ionic solution, ions dissociate as they dissolve, creating more solute particles. So what this means is when salt dissolves in water, it breaks up into its parts: sodium and chlorine. That means I have 2 ions, I equals 2. When magnesium chloride dissolves in water, it also breaks into its parts. I have magnesium and I have chlorine. Oops. But this formula tells me I have 2 chlorines. So I have 1 magnesium, 2 chlorines, I equals 3. I don't even have to do this dissociates into that to find I. All I do is take my ions, so in this case magnesium and hydroxide, circle them because that really helps with the polyatomic ions, and I have 1 magnesium and 2 hydroxides. I equals 3. and that's how you find I. Circle your ions, add up your subscripts. I is 3. Now for covalent solutes, technically we say we don't need I, and that's because I is always 1. They do not dissociate as they dissolve. So some examples, we have sugar, we have ethylene glycol. Remember, covalent is no metals. And remember, ionic is metal and non-metal. So sneak in a little review everywhere we can. So ionic, you recognize because it has a metal, sodium, magnesium, magnesium. So those dissociate into ions. Covalent you recognize with no metals, carbon, hydrogen, oxygen. None of these are metals. These are covalent compounds, so always I equals 1. Or you could say you don't even need to use an I. Either way, it means the same thing for covalent solutes. Okay, so let's do a couple of examples. The first one will be a freezing point depression example. So the first couple of things you want to do is pull out the important information in the problem statement. So I'm trying to find the new freezing point. So the first thing I'm trying to find is delta T, the change in temperature. I'm given KF, it's down here. I need to find molality, and I need I. To find I look at the formula. Is this ionic or covalent? It's covalent, so I equals 1. Okay. Now I have KF, I have I need molality. We go back to our triangle, our definition. We have M equals moles per kilogram. That's a horrible triangle. You get the idea? I'm trying to find molality. I cover up the molality. I need moles of solute per kilogram of solvent. So small number is solute, 50 grams. I want to convert that to moles. I'm going to kind of set this up to remind me that's what I want to do. And I'm going to take 200 milliliters and convert that to kilograms. Small to moles, big to kilograms. So 200 milliliters, remember, for water. Milliliters is the same as grams. So 200 milliliters means I have 200 grams, which is 0.2 kilograms. Okay, so I have kilograms now of water, and I need moles of my solute, which is, actually this is table sugar. So, sucrose. I have 11 carbons, I have 22 hydrogens, and 11 oxygens. That gives me a molar mass of 330 grams per mole. So if I plug all of this in, 50 divided by 330, it gives me 0.15 moles. So I have moles and I have kilograms. 0.15 divided by 0.2 gives me 0.76 molal. So now I have M. Plug it in. Delta T of freezing is KF 1.86 times M, which is 0.76, times I, which is 1. I have 1.86 times 0.76 times 1 gives me 1.41 degrees. Now this is my delta TF. So remember, freezing point depression. So I want to know what the new freezing point is, so I have a little bit more work to do. Freezing point, for this case, for water is 0, right? Minus 1.4 is the depression. It gives me a negative 1.4 degrees Celsius. That is the answer to my question. So this number tells me how much it changes by. I know freezing, depression, temperature goes down, so I take the regular freezing point of water, which is 0, and subtract the change, which is 1.41, and I get negative 1.41 degrees Celsius. Let's do another one. What's the new boiling point when 10 grams of calcium chloride is dissolved in 200 milliliters of water? Okay. Again, I have KB. I need to calculate M. Let's go ahead and talk about I real quick. I have calcium and I have chlorine. I have 1 calcium, 2 chlorines, so I equals 3. Now let's calculate molality. Take the small number, the 10 grams, then that gets converted to moles. Just to remind me what I'm doing here. And then the 200 milliliters is the same thing, and 200 milliliters convert to liters. Sorry, milliliters is the same as grams, and then I convert this to kilograms for molality, because remember, let's draw my triangle a little bit bigger here. Molality is mole divided by kilograms. Okay, so I have getting moles from the small number, kilograms from the big number. 200 milliliters is the same as 200 grams, is the same thing as 0.200 kilograms of water. So now I just need to do this conversion. 10 grams converting to moles. Calcium is 40.08 plus 2 chlorines that are each 35.45 gives me a molar mass of 110.98 grams per mole. 10 divided by 110.98 gives me 0.09 moles. Now I can find molality is 0.09 moles divided by 0.2 kilograms, which gives me molality equals 0.018. Now I can plug it all in. Delta T equals KB, which is 0.52, times molality 0.018 times 3. 0.52 times 0.018 times 3. Delta T equals 0.03 degrees Celsius. Not a huge temperature change here, because that is a relatively small amount of calcium chloride. So, delta T again though is what I got. It's boiling point elevation. So our new T of boiling is our initial boiling temperature of water, which is 100, plus our delta T, because it's elevation, it's increasing. So I get 100.03 degrees Celsius. You'll notice based on the constants, especially for water, the effect of boiling is not quite as high as the effect on freezing. The constant tells you that. The last one is more of an application. This is like if I want to change the freezing point by this many degrees, how much sodium chloride would I need to add? Okay, let's delta T equals